大家好，我是曾志伟。怎么样？这个领子屌不屌？算了，不这样的还真傻逼。开始学习了啊！
So we're coming along here for value of d, etc., and coming along here, 0.165. Now when you then substitute value for the SU over gamma h times the factor of safety, you find the factor of safety
鸡巴卡，操！
is equal to 0.61. So obviously it's definitely going to fail because it's less than 1. In our previous example here, we had a factor of safety, I think we calculated from this. It was also going to fail. It was about 0.93. But in reality, you say this is actually quite close. NS would equal to 0.165 from our particular chart for value of data. Data is 37 degrees. Data, last one here, is 37 degrees. So we're coming along here for value of d, etc., and coming along here 0.165. Then substitute value for the SU over gamma h times the factor of safety. We find the factor of safety is equal to 0.61. So obviously it's definitely going to fail because it's less than 1. In our previous example here, we had a factor of safety, I think we calculated from this. It was also going to fail. It was about 0.93. But in reality, you say this is actually quite close to being in a stable situation, whereas the critical failure surface here is showing that you've definitely got a failure taking place. So the main message is that you can choose one hypothetical or postulated failure surface. It's not going to give you the actual factor of safety until you do a whole series of different calculations. So, and this is just one example of where you can actually get an exact solution, and that's for the excavated cutting example. Okay, so that's one example, and I'm going to talk you through. The next is, I suppose I'll just keep on the subject for the practice session here. Again, you've got solutions for that. Now, the factor of safety, in general for translation of slip is equal to c dash over gamma z times sine beta times cos beta plus tan phi dash over tan beta equals 1.
Fuck you！ 我他妈这过程中能不能把这个网给切掉？操他妈的！
Gamma W times H over gamma W times phi. Gamma Z
操你妈！老子大不了不播了，他妈傻逼！我靠，搞你妈蛋！我操！真他妈有病！你他妈能传不了，他妈去鸡巴鸭子！C
squared. It wouldn't be, you may actually, I'll talk you through. various components of that equation. But that's assuming, and you've got to understand it because you might be given an equation like this in an exam, for example. So you need to know the relevant important terms to use in that particular equation. Now, this is for translational. You need to know what a translational slip surface is, and you know that it's only relevant to that translational mechanism. Now, what are the terms in this equation? The first term, and it's made up. The first term here is z, just to be aware of. Z is the depth.
你卡你妈了个逼呀！我操你妈！
The first term here is z, just to be aware of. Z is the depth. Z is equal to the depth of postulated planar.
靠那娘！
That slip surface can be anywhere. It doesn't matter, in the example in your back section here, we could have a slip directly on the surface, we could have a slip within the sand, we could have a slip just above the liner for this landfill condition, or we could have failure within the actual rock material itself. So if you've got an equation like this, you've got to acknowledge that you've got to look at all potential slip surfaces. And in this particular example equation, the first channel, it wouldn't be, you may actually, I'll talk you through the various components of that equation, but that's assuming, you've got to understand, because you might be given an equation like this in an exam, for example. So you need to know the relevant important terms to use in that particular equation. Now, this is for translational. You need to know what a translational slip surface is. You know that it's only relevant to that translational mechanism. Now, what are the terms in this equation? The first term, and it's made up. The first term here is z, just to be aware of. Z is the depth. Z is equal to the depth of postulated planar. Slip surface. That slip surface can be anywhere. It doesn't matter, in the example in your back section here, we could have a slip directly on the surface, we could have a slip within the sand, we could have a slip just above the liner for this landfill condition, or we could have failure within the actual rock material itself. So if you've got an equation like this, you've got to acknowledge that you've got to look at all potential slip surfaces. And in this particular example, we could have a slip surface within the sand, as I said, on the between the sand and the liner, or even between the liner and the rock, or even in the rock itself. So we've got to acknowledge that those potential failure surfaces can exist. Now, when we look at this equation, we need one thing, important thing to note is that when z is the maximum, fs is the lowest value. So if we're looking at a failure occurring within the sand layer here, there's no point looking at a layer halfway within the sand, because z is actually, we know that z is going to be smaller. Sorry, fs is going to be smaller when z is not. As it happens in this case,
我他妈的个逼！
to actually go and say, well, what potential z values can I have? And in this particular example here, you've got a z value corresponding to the bottom of the sand, you've got a z value corresponding to the interface between the sand and the line. Okay, that's the z value. The next value to note that's very important is this h value. And h is the height to which water would rise in the standpipe on a particular postulated failure surface. So, I might put this in a second, but so if you've got slope postulated failure. So, come back to this in a second, but if you've got a slope, so again, if you've got a failure surface that looks any arbitrary value here, right? This is, you're looking at some planar surface here. Now, the water, if you place a standpipe piezometer at that location, all that does is measure the water pressure at this particular point. And the value of H is the height to which water would rise in that particular standpipe. So at point A, the core pressure, which is obviously important in all of these equations, is equal to gamma W times H. So as it happens, in our particular taxation example on Thursday, we didn't have any H, so it was completely dry, so that component of the equation disappeared to zero. But it's important in general to understand that your value of core pressure and the factor of safety is dependent on that value. Now, if I can find your notes, you have there's an example in your notes, well, loads of examples, but one of the examples would be, for example, one example, when we had a slope, if we had a phreatic surface, the surface of the water is called the phreatic surface, and when the water is flowing, it's usually called the water table when the water is not is static. So on slopes, almost inevitably, water is present, it's going to be flowing down by gravity down the slope. And these are the equipotential lines associated with that. If you draw a flow net associated with water, you might have the soil surface might be here, for example, the phreatic surface can be below that point. And the value here, if we imagine a failure surface that is along this is a flow line. These are flow lines here. And these are so-called equipotentials. The water is flowing down here, and you're getting, for that particular, these are squares, because you've got a homogeneous soil and this is your flow. Now what this example would show you is that if this was if this is our, I'm just going to write down here, this is our postulated failure surface. We put a standpipe at that location. The actual water will rise to this exactly where this line comes across. This point here, the potential at this point corresponds to the potential at that corresponding along everything along this point is at the same potential. So it means that the water will rise to a distance H in that particular example. Now we'll say, well, what is H? You can actually work out H. If you look at a situation here where I just draw out the scale and you've got a surface like this. Remember, this is a right angle here, and this is a right angle here. So if this distance here, we say is equal to z, then this distance here, this angle is beta, because this slope is an angle beta. And this is all kind of covered already, you know, so this is kind of more revision. But this is z cos beta, this distance, and this height here must be equal to z cos square beta. And therefore, in this particular example, where you've got the water level and here, you've got u is equal to gamma w times z times cos squared beta. And that's just one example. So when you substitute back into your general equation, which was given here, when h is equal to gamma wz times cos squared beta, you can see that you'll end up that h will cancel with this amount here, and the actual you'll be left with an equation tan pi and tan beta into 1 minus gamma w over gamma when the water table or the free surface is coincident with the surface of the solid. But in general, it's good to just have this in your mind that the h can actually be variable depending on various conditions. Now we did also have a I've got a copy in your notes here. We also looked at cases where the water level was at an angle alpha to the horizontal, and it was impinging directly on the actual slope, and we ended up with a different expression for the value of h, and that enabled us to then derive a general equation for the actual factor safety for that particular case. I'll just show you that. So that's what we did in this particular example here. You can see we've got, in this case, we've derived the value of h, just in general for that equation, and then we substitute back into our general equation to find this equation. So that enabled us to look at factors of safety associated with different flow lines. We've just looked at the case where alpha is equal to beta, where it flows down parallel to the slope. But in general, it could be at an angle alpha, in which case you'd end up with a different expression here for h, a more general expression, and that gives you, if alpha is equal to beta, that's 1 plus tan squared alpha, which is equal to sec squared alpha, which is equal to 1 over cos squared alpha, so you get h is equal to z cos squared alpha. It's exactly the same as the other expression when beta is equal to alpha. But if it's in general, this is what you get when you input your value of h. So just to summarize, so that's obviously an important term here, h, where you've got water pressure. Now, so that's a general equation, and in your particular example, you were asked to determine if a translational slip would occur when the angle is 32 degrees. So we looked at 3 different examples. One was where the sand was above. Is this the right example? There's no water present, and we get, and hopefully that's the right solution to the problem. I think it is. We end up getting, we look at different factors of safety, and we've got a factor of safety associated with along the surface here and just above the membrane and between the membrane and the sand. And usually when you're building these landfills site, you always put a liner, and this is a cover there. You have over the liner when you're building any of these domestic municipal waste dumps. And this liner is always the critical. This is obviously very good at making sure that you're not getting any further infiltration into the waste fill. But also, it's obviously a point of weakness with regard to ensure that you're not getting any further infiltration into the waste fill. But also, it's obviously a point of weakness with regard to overall slope failure. Okay, so that was an example you've already seen. So I just want to run through another example here, which I'll post on the web. So this is post on LMS. So this is a case. So this is an example of where we've actually using.
我他妈操你妈！你他妈在砍你妈呢！我操！
Of our particular or excavation or whatever we're doing. So very often soil layers like this will be used in applications where maybe you've got a weak rock present, and you put soil layers in, excavate further down, put another soil layer in, and this is the general equation associated with the actual failure associated with that with that situation. Now, in terms of this question here, whether or not you're asked to prove it or not, I doubt it. But what is it? You might be asked to explain some aspects associated with factor of safety, even though it looks like quite a complicated expression, is really just looking at the overall shear along this potential failure surface. So this potential failure surface is at an angle theta to the horizontal, and what you're looking at are the various forces along that slip plane. Now, in terms of the actual driving force, as we have in all of our slope examples, we've got our weight. Our weight component is actually causing our slip to occur. So what you've got is essentially, in terms of the actual disturbing forces, you've got some force associated with W here, and W times the sine of that angle will give you a force along this failure surface here. Component of W along that failure surface is W sine theta, and that is actually driving shear. So W is very high, you can imagine. You're going to drive a lot of shear along that surface here, and that needs to be resisted by the actual soil shear strength. And obviously, you would iterate your problem depending on your value of theta to derive a critical mechanism associated, because obviously the factor of safety for various thetas you would look at. And you find the one that is giving you the lowest factor of safety with theta. So, but in general, if we have a theta value here of this particular number here, we've got this driving force W sine theta, which is coming along this particular failure surface here. Now, what is the important thing to note is, okay, that's a pretty standard example for, and you would imagine it's very similar to sort of a typical active weight behind a retaining wall, for example, that case. But in this particular case now, we're also introducing a sewing nail. So if I actually look at what the sewing nail is doing. So this is our potential failure surface. And we've got some sewing aid that comes at this particular angle, which is an angle of alpha. And our potential failure surface here is equal to theta. So this angle here would be theta. This angle here would be equal to alpha. So we now have, if we look at the two components of this force T. So we've got one component, we look at a right-angled triangle associated with this here. We've got a force T times the cosine of theta plus delta, theta plus alpha, is along is the component of T along the failure surface. Along failure surface. So we can see that in itself is contributing to the actual stability, because we've got a component acting up in this direction, opposing the weight component of the force along that failure plane, which is trying to drive failure. And that one component, but the second component, which is actually often more important, is the normal component. So T times the sine of theta plus alpha times the tan of phi. So if we look at this component here, this is the T of sine of theta plus alpha here. And that's a normal force, and a normal force times the coefficient of friction generates shear stress. So essentially, you're holding the two sides of the wedge separated from, you're separating the soil on one boundary, one side of the wedge to the other, but you're actually tying them together by using this soil reinforcement. And that basically is, you've got the T sine theta alpha component, that's the normal component, and we know then the friction and resistance generated by that normal component is that normal component times the coefficient of friction. So these two components are important to be aware of, is how actually you know that sewing nail is giving you overall stability. Because if you now look at the equation up here, you can see in terms of the resistance, all of these terms here are resistance terms up here. Driving at the bottom of here, this is like this is actually causing failure, and this is all of this is resisting force. Force on the shear. So we can see we've got these two components, this one and this one now associated with one single sewing nail. Very often you've got more than one sewing nail, and you may have like maybe 10 different levels of sewing nails, for example, and that will give you an overall, obviously, big resisting forces. And then you've got all these other components here, which are associated with the component of W, which is normal, which is parallel to the, which is actually, sorry, component of W, which is causing an additional stress, normal stress on the actual failure surface, and that also gives you an amount of stability. So now we look at an example with something like this. And in this particular example, we're told that sewing nails are dipping at an angle of 20 degrees. That means that angle alpha is equal to 20 degrees. And with a tension capacity of 50 kilonewtons. So these nails are extended far enough beyond this failure surface, and they can anchor in properly into the soil. And they've got a tension capacity, the value of T, here of each of those of 50 kilonewtons. And they're used to provide stability to a 10-meter high cutting in a material with an unbent shear strength of 100 kPa. So SU equal 100 kPa. Now, very often, if we have, you'll see a term called the unconfined compressive strength. It's almost always used for rocks, for rock. So this could be a weak rock. And what from the Moore circle stress, you can say that the unconfined compressive strength is twice the unrated shear strength. So we could alternatively say this, that the rock that we're trying to stabilize has got an unconfined compressive strength of 200 kilonewtons per square meter, which would be a very weak rock impact. So we're asked here to assume the critical active weight is inclined at 45 degrees to the vertical to determine the number of soil layers we need to actually provide a factor of safety of 2 against failure. So
哥伦比亚又咋回事了？Land Cruiser。
what we need to do is obviously determine, it's quite a straightforward example, but we need to obviously use this equation here to do that calculation, but actually only use, and to apply that equation, we need to know what each of those terms are present. Now, first thing to try and eliminate, because I remember in previous years people ended up getting mixed up, this Q value here is equal to 0. This is just an additional vertical force applied on the surface of the weight. So, generally speaking, in most cases that would be equal to 0. But you could have, you could have a house foundation, or you could have a crane located near the top here, where you need to add this additional vertical force to your weight, and that's obviously going to lead to more instability. But in our example, we haven't got any value of Q. Now, in our case, because we're doing an untrained analysis, or often called a total stress analysis, because we're not using effective stresses, we can model our clay as SC, C dash equal to SU, and phi dash equal to 0. So, as we've done before, for many undrained calculations, both for retaining walls, for bearing capacity problems, and for shallow foundations.
我靠，为啥鸡巴会等于0啊？学了他妈30多分钟，操！我以为学了1年呢都。
We've said for undrained conditions, we're going to model the material, the friction angle of 0, and the C dash value of SU. So that means when we come back to this equation here, we know, for example, that if we look at the various terms here, H is equal to 10 meters. C here is equal to our undrained, H is equal to 10 meters, and C is equal to our SU value, because we have set C dash equal to SU.
他妈操！
Theta is equal to 45 degrees. We've been told that the look at the critical failure wedge, which corresponds to a typical failure wedge angle for an undrained case at 45 degrees. So we have all of those terms. We calculate the weight W as being the width. Weight of this wedge of soil, which is basically half the base times the height times the unit weight of the soil, which is of the rock of 22 kilograms per cubic meter. That gives us a value of W. and we know our tan5 value. And then we know we can calculate these various other terms. Theta plus alpha, we know theta is 45 degrees, we know alpha is equal to 20 degrees, and we know our friction angle here, this term is going to be equal to 0, so the tan5 is equal to 0.
你他妈又卡死了，我操！
This is all this term will go to 0, and this term here goes to 0 as well. So we're left with just the rest of the terms.
你他妈还让我看不让了，我操！
5 is equal to 0. So this is all this term will go to 0, and this term here goes to 0 as well. So we're left with just the rest of the terms present here. So I put this example under it goes to 0 as well. So we're left. This term is going to be equal to 0. We know theta is 45 degrees. We know alpha is equal to 20 degrees, and we know our friction angle here. This term is going to be equal to 0.
那为啥可以他妈是 zero？ 我靠！
And phi is equal to 0. So this is all this term will go to 0, and this term here goes to 0 as well. So we're left with just the rest of the terms present here. So I put this example under work example on LMS in a minute. You can see here what we're defining how here is our factor of safety is equal to 2. So this number is equal to 2. We've calculated our various values of, this is not show all of those terms, calculate the various terms, all those tan5 terms are equal to 0. You just left with cos theta plus alpha term here. And you end up in this calculation here.
有些同学不像话。有些同学不像，有些同学们不像话。还有什么？男女同学花前月下，成双入对，简直是不想学习了。有些同学不像话。男女同学花前月下，成双入对，简直是不想学习。
Requiring t value, instead of actually looking at, you assume that you've got, for example, because this is the sum of all of these individual anchors, you just assume a total anchor force T here in this calculation, and that means you need a T value. So in other words, you're saying this is equal to T, instead of saying the sum of each of the individual TIs, you say it's T cos theta plus alpha plus T times sine theta plus alpha times tan phi, and this is 0 anyway. So you get T from this equation, and that's the total value of T. And we're being told that the anchor capacity is only 50 kilonewtons. So that means that if we need a total value of T in this equation here, which is the total force tension from each of those sewing nails, is 330. kilonewtons, then we need 50 into that. So obviously we need 6.69 nails. So obviously you kind of 0.69 nails. So you need 7 nails within your excavation to actually go and produce the buildings. They would look a bit like that: 1, 2, 3, 4, 5, 6, 7. Within your 10-meter slope, so they'll be separated, roughly 1.5 meter centers down vertically to actually ensure that vertical cutting within that material is stable. And that example, and one other example, I think that I'd probably within your excavation to actually go on total value of T. And we're being told that the anchor capacity is only 50 kilonewtons. So that means that if we need a total value of T in this equation here, which is a total force tension from each of those sewing nails, is 334 kilonewtons, then we need 50 into that. So obviously we need 6.69 nails. So obviously you kind of 0.69 nails. So you need 7 nails within your excavation.
你他妈都不带动的，我操你妈！
They would look a bit like that: 1, 2, 3, 4, 5, 6, 7. Within your 10-meter slope, so they'll be separated, roughly 1.5 meter centers down vertically to actually ensure that vertical cutting within that material is stable. And with that example, and there was one other example I think that I'd probably I can show you. Okay, so coming back to the typical translation type surfaces here, and I've got another example which is again very similar to what you've done already, but it just gives you more practice in trying to apply this equation. So In this particular example here, we've been looking at, we've got water phreatic surface at ground level here, and we've got various, obviously we've got sand, overlying clay, and we want to look at basically, in this case, the question is what value of data here will give us the factor of safety on shear strength of 1.25. So in this case here, you know everything, but you don't know the value of data. So you need to go, and obviously the factor of safety we're saying is equal to 1.25. So what you need to do, probably the main thing in this first example here, the big unknown in this is to say, well, what is the value of H to input into my various types of potential slip surfaces? Now, in all of these cases, we can basically assume that we've got grain condition. And we've seen already with
他妈几个题我操！Determine the slope angle that will provide a factor of safety. Shear strength.
the derivation, that H is equal to Z cos squared beta. So to do this problem, you have to prove that H is equal to Z cos squared beta, and I did that proof somewhere already. And here, so that's basically assuming when you've got this phreatic surface flowing parallel to the surface like that, U is equal to gamma W times the H value, which is Z cos squared beta. So once you have that particular here example here, you can then go and calculate values of you then, unfortunately, because it's a sort of a non-linear problem, it's easiest to solve this problem just by trial and error. So you need to go and input into your problem various values of data to give you a solution. If you can find the solution here. And again, this is all going to be on your. It's on the web page anyway, it doesn't matter. So what I'll do is, so basically we'll look at various values. We've obviously got one failure surface here, which is within the sand, and Z value is equal to 1 meter. We need to look at the value, the stability associated with that. There's no point looking at a failure in a strong rock, because you wouldn't get a failure. By definition, when you say strong rock, you're not going to get any the factor safety is enormous in those situations. But in the clay layer with this properties, you basically need to go and use an equation where if you remember, you need to make sure that you're using a Z value as the maximum value. So you're looking at the Z value just below here. There's no point looking at surfaces in between at various depths, because your equation, your factor safety, is going to be lowest for that value of highest value of Z. So you can find a sheet of paper again. Yeah, here. So with Z is equal to maximum, obviously with the C dash component as well as with the water component. As Z is highest, you're going to get lowest factor of safety always. So essentially, you're in this example here, you're looking at this value of Z. You only need to look at those two particular potential various surfaces to work out what is the value of beta to give you that factor C. So you would do that by trial and error to give you your value of beta. Don't try and solve the problem this non-linearly. You can work out approximately, because it's a non-linear equation, you see beta is here and here and here. It's a bit of a pain. So just basically look at substituting in a couple of values of beta, and like if that was an exam situation, if you just did one or two, demonstrate, then that would be sufficient, because we know we can eventually get to the solution by that cover some examples. They're all more or less similar. And the two types of there's all of the types I just talked about, kind of examples you might be examined on. But just bear in mind that this is just one component of slope stability calculations. There's more work to more applications when you look at seismic loads, etc., which are very important when it comes to slope stability. Other aspects, all generally solved using computer analysis in computer software. But these types of calculations that you're learning in these units are absolutely vital to understand, because every engineer will actually go and apply these simplified techniques initially to see if there's actually any kind of stability issue. So this week we still have on Wednesday we have a lecture on Wednesday, starting off on a different branch of the I think it's consolidation and soil improvement. And on Thursday then there'll be a standard fact session. So we're getting towards the end of the unit. So anyway, so that's it for today. Okay?
I know that we are getting close to the end of the unit. Ah, 如果说连任呢，连任有相等的法律呀。连任有相等的法律呀。看一下动主直播，我这个还能上传不能？哼，这他妈是传不了的，我操！滚！还你妈逼！不对劲啊！不再打，不看。有吗？我讲。
So we firstly look at the process of consolidation. So one would be aware of the fact that actually the world is three-dimensional. So we need to look at all three dimensions. But we can first of all look at one-dimensional consolidation, which is basically involving, and this is applicable to, for example, underneath a large road might be constructed on soft clay deposit. The conditions are quite close to being one-dimensional, or a large raft foundation supporting a building. So in under one-dimensional conditions, basically there's no lateral strain. We've got conditions which are simply one-dimensional in the vertical direction. If we can imagine this sort of boundary condition that you're familiar with, maybe from your last year's geomechanics. If you've got a drainage here, this is like your clay material. It doesn't have to be a clay, right? It can be any soil here. We're not going to do this today. And so you've got a drain up and bottom. And say what we do is we apply an increment of vertical stress to that element of soil which is constrained from moving laterally, or vertically, or sideways. But it also has got a drain located at the top and bottom of the sample where water can just freely escape into. So if we apply that vertical stress delta sigma Z, what happens if you, irrespective of whether you've got a clay or even a sand, it'll happen instantaneously in both materials. Then immediately, because there's no time for water to escape from the voids, which could be like a millisecond if you're thinking of a sand, or could be like a long time if you're thinking of a clay, irrespective, you get an increase in pore pressure equal to the increase in vertical stress which you apply. So if you apply an increase in vertical stress of 50 kPa to your sample, you're going to get an increase in pore pressure immediately equal to 50 kPa, because the water, if you can imagine, the only way that actually you're going to get pore pressures less than that number is if you get some drainage away of water within the soil. So immediately, that's actually the initial condition. So that's stage one. Now stage two is basically what happens is the excess pore pressure will increase in core pressure within the void of the soil. And
他妈的，这不是他妈 zero 吗？我他妈的3009他妈的得记一下。delta U 等于
that core pressure will dissipate. And why will it dissipate? It will dissipate because if you've got a high pressure here within the soil, and adjacent to that you've got a low pressure, water will flow from the high pressure zone to the low pressure zone, and subsequently it will just dissipate out from the soil until finally there is no further excess core pressure in the soil. So in that situation, in this case I probably should write here, delta sigma Z prime is equal to 0. That's because delta sigma Z prime is equal to delta sigma Z minus delta U. So, initially or instantaneously we apply an increment of stress to our material, we're not going to get any change in effective stress. However, if you then allow some time for the material to drain, you're going to get delta sigma Z prime is essentially going to equal to is equal to delta is going to equal to delta sigma Z after delta U goes to 0. So we get an increase in effective stress in the soil, but that doesn't happen instantaneously. Immediately, there's no change in effective stress. We're only getting a change in effective stress after all of those excess core pressures have dissipated. And that's the process of consolidation. So the process of consolidation, what you may be already familiar with, is where the water is squeezed, excess core pressure is squeezed from the soil, you get water flowing out of the soil, and that process is the process of consolidation. So just write that down here, process of consolidation involves the dissipation, or reduction in excess core pressure and subsequent increase in effective stress. Now, what you're doing is and so involves, just write that down here, process of consolidation involves the dissipation,
3年了，我都想死你了。最对不起的就是范厨师。多好的人呐！
dissipation or reduction in excess pore pressure
我某个人又重新加回来了。
subsequent increase in effective subsequent dissipation and subsequent dissipation or reduction in excess pore pressure and subsequent increase in effective stress. Now, what you're doing is you're, and associated with that pore pressure dissipation, I should probably point out that you're getting flow of water out of the soil. That's what you're getting at dissipation. You're basically squeezing water. So underneath, for example, underneath a large embankment, if you were building a road, and embankments, maybe typically of the order of 10 meters high, 5 meters high, you can, by placing that embankment, you can end up squeezing large amounts of water from the actual soil due to that process of pore pressure dissipation. So much so that you actually have to install pumps to make sure you pump away all that water that's being squeezed from the voids. Now, associated with that, but that's not the actual excess pore pressure dissipation leads to that change in effective stress, and when you get a change in effective stress, you get settling. So that's what we're going to end up looking at today. We're looking at the consolidation equation, how we can work out how much the pore pressures are dissipated by, how the effective stresses have changed, and subsequently how much the soil has actually settled. I suppose while I'm just on the subject here, just to remind you, is in terms of settlement, what kind of train we normally see if we plot settlement. So we've got time here to log scale. So this might be like 1 minute. This might be like 10 minutes. 100 minutes. This is just to give you an idea. Obviously,
10,000.
Depends on that's what a log scale would look like. So initially, your settlement you won't have any change in effective stress initially. Initially you're going to be up here and you're going to be a fairly flat line until all of a sudden your pore pressure starts dissipating, your effective stresses start increasing, and you end up following a line that may look like something like that. And that's your typical semi-log type variation of settlement with time. Now normally, at some point here, there's at this point, delta U is equal to 0, sigma Z prime is constant, and this is called the aim of consolidation. Now, in reality, actually, you have to go to infinite time to have every excess pore pressure component dissipated, but normally we consider the aim of consolidation where roughly 90 or 95% of the excess pore pressures are dissipated. But this is the kind of training we have with log time. So what is it that's causing, because there's no increase in effective stress from this point onwards, what's causing this additional settlement? And that's called creep, where creep on the soil, every material you come across, whether it's steel, what's causing this we have with log time. So what is it that's causing, because there's no increase in effective stress from this point onwards, what's causing this additional settlement? And that's called creep, where creep on the soil.
Creep.
Every material you come across, whether it's steel, concrete, and whatever timber and soil, will creep over a given amount of time. Some surfays, the creep component can be actually very large, and we need to allow for that in our calculations. But and maybe that scale might be, this creep going for many years over the lifetime of a particular structure. Okay, so ultimately, that is the kind of variation of the training that you will have seen before when you're looking at things like one-dimensional compression tests in odometers. You get this kind of training. And what you're seeing here is the pore pressure dissipating. And as the pore pressure dissipates, the effective stress is increasing. So sigma Z prime is increasing all the time. And up to this point, at each point, it's constant. Sigma Z prime is constant. So that's important to be aware of that we have that additional creep stage at the end of consolidation. Now, the actual equation we're going to look at try and solve in this lecture is given here, which is the one-dimensional consolidation equation. And this is given as, now in this equation here, because it's difficult to write delta U, U is equal to the excess pore pressure. It's not total pore pressure in this consolidation, differential consolidation equation. So some sometimes people will use subscript E next to the U, just to denote the fact that you're not looking at total pore pressures in this equation. This equation is giving you the excess pore pressure. And what it will give you is the excess pore pressure here as a function of depth, which is Z, and a function of time, which is T. So where does this equation actually come from? And there's two components which are giving rise to this equation. The first of these components is simply Darcy's law. And Darcy's law will tell you that the secret velocity V is equal to the permeability times the hydraulic gradient. And what is the hydraulic gradient? It's the difference in head from one point of a particular location to the head at a different location. So if we look back at our example here, when we've got water flowing from our sample here, we're going to have a high head here in the initial part of our sample. We're going to have a high value of water head. And water head in that case, I'll just write down here, water head in that case will equal to delta U over gamma W. So rather than describing pore pressure in terms of actual excess pore pressures, very often we use the term head because that's what the Darcy's equation is written in terms of. It's giving you the flow delta U of a particular location to the head at a different location. So if we look back at our example, here, when we've got water flowing from our sample here, we're going to have a high head here in the initial part of our sample. We're going to have a high value of water head. Now, water head in that case, I'll just write down here, water head in that case will equal to delta U over gamma W. So rather than describing pore pressure in terms of actual excess pore pressures, very often we use the term head because that's what the Darcy's equation is written in terms of. It's giving you the flow as the permeability times the hydraulic gradient, and that I value is equal to H over L, where H is the head loss over a certain distance L. In this case here, we've got a given amount within the entire sample here. We've got the initial head value of H and the length over which that hydraulic gradient is changing. And the length over which that's changing is actually different for different parts of the sample, whether you're in the middle here or at the edge, etc. But so we end up, you can imagine, by looking at this equation, you can imagine there's a flow of water out of this sample just simply arising from that Darcy's equation. Now that's one side of the equation. The other side of the equation is the volume change due to an effective stress change. And so in a one-dimensional situation, for example, the vertical strain is equal to the change in vertical effective stress over the Young's modulus. And now the rate of change of the volume with respect to T, so V is the volume, is equal to, because it actually write down volume would be EZ times, for example, dz times dx dy, would be the actual overall volume change. The dV, dt, you don't have to derive this or anything, but the volume change associated with here would be dEz dt times the actual incremental, and the actual strain dEz dt would be equal to d sigma dash z dt over the modulus. So this is just equal to, if you can look at it the other way around, this is stress is equal to Young's modulus times strain. Now, delta sigma z prime is equal to minus delta u. That's because under our conditions, boundary conditions we've got under application of any given increment, the amount of the amount of change of vertical effective stress you have is equal to the excess pore pressure change. So that's what we saw in this equation here. Delta sigma prime is equal to delta sigma minus u. So under the conditions we normally have, we've got constant vertical stress. So basically you can see that delta sigma z prime is equal to minus delta u. So that means that this equation here then reverts to minus 1 over E times du dt. So that gives you one part of that particular equation. The other part is if we now look at this equation here, the dz can be written as equal to minus k times du dz, and we have to change from k to the pore pressure is minus k over gamma w times du dz. Now that's one side. As I say, the other side is associated with the actual effective stress change associated with our soil here. So this gives us so this term here can work out, well, probably I probably should derive the whole thing, but I don't really want to derive the whole thing in this lecture. It's in any standard textbook. But what I want you to realize is all you're doing here is you're actually equating the volume change due to the flow of water out of the soil to the volume change associated with the effective stress term. Now, the volume change due to the flow of water and the hydraulic gradient is related directly to Darcy's equation, which is related to the permeability K, whereas the actual settlement of the soil is related directly to the Young's modulus of the material, the settlement of the volume change associated with that effective stress change. So when you combine both of those terms, again, all I really want you to understand is why where this equation comes from. You get an equation where CV, some people use that term MD, but I just want to call CV, it ends up being K times E times the actual weight of water. So in this particular equation here, this is the general equation. Please have a look yourself if you're interested, but it's more important than you're not expected to derive this equation. It's more important you understand that the actual equation arises from both of those particular components of volume change occurring within your sample. One associated with the effective stress increase, and the other associated with squeezing of the flow of water, how fast water can flow out of the soil. So ultimately, the actual process of consolidation is not simply one of flow of water from the soil. It's also got to be matched by effective stress and changes associated with volume changes associated with changes in effective stress. So that's why we come up with a CV. This equation, this CV term here, is actually a result. It's actually the product of the thickness of the soil, calling the settlement, and K, which is the actual flow and permeability of the actual material. Both of those values combined to give you this so-called coefficient of consolidation. Now, in this equation here, this is the rate of change of excess pore pressure with respect to time, and that comes from the actual equations here we've just seen in terms of the volume change. And the d2 UBZ squared term comes from the actual volume change due to Darcy's law. And that's the equation we have. The one-dimensional equation, when you go to 2 and 3 dimensions, it's very, very similar. So if we can solve, and we can talk about that later, if we can solve the one-dimensional equation here first, and have a see, and we can then at least try and solve problems involving one-dimensional flow. So the equation we want to try and solve is one where we've got this is the equation we want to solve. U is the excess pore pressure, and U is a function of Z and T. So we need to solve that equation subject to whatever boundary conditions we're looking at. And one of the useful things about this part of the course is that we use the finite difference method to actually solve this equation. And this method is extremely powerful to enable you to solve other partial differential equations just using an Excel spreadsheet. Because all we're doing is we discretize our problem into a series of nodes. So in this particular problem here, what we look at is we try and represent the du dt terms and the d2 udz squared term numerically. And to do that, we first of all divide our problem into a series of nodes. So we've got nodes here, each has an equal spacing equal to delta z. So whether we could have a soil, this could be an odometer test, could be a large body of soil, and what we've done is we've divided it into these different nodes. And we're starting off with node I equal to 0 at the surface, and at one boundary, and at the bottom boundary we've got another node here equal to I is equal to n. So these are nodes which we need to describe in the solution of our problem. And that's where we get the solution. We determine the excess flow pressure at each of these nodes in our solution. So now how do we actually represent, how do we calculate now? We use the notation U, comma ij is the excess flow pressure at node I, and I just talked about where those nodes are, at time increment j. So what we do, we start off with time equal to 0, and then we go to time t plus delta t, t plus twice delta t, and this is increment 0, increment 1, increment 2, etc. So if we wanted to find out the excess flow pressures at a given at 3 delta t times, if we choose a delta t value, and we want to find the excess flow pressure 3 times delta t later, then we need to do an increment. We need to actually solve our problems at t plus delta t, then use the solution for t plus delta t to find a solution of t plus twice delta t, use that solution to find a solution of twice 3 plus delta t. So if we now define, so this would be, for example, this would be the flow pressure at time increment j equal to 3, and we've got solutions at each of these nodes corresponding to node I, for example. So what we do is we now simplify or approximate, our first equation. You can see we want to solve this du dt term here. We now can represent approximately delta u dt is the rate of change of excess flow pressure with respect to time. Now, what that means is that basically it's the flow pressure at a given location I, so that's location I and location I, at time increment, the next time increment minus the current time increment divided by the time between those two time increments. So this is so this could be, for example, the excess flow pressure twice at time t plus twice delta t minus the excess flow pressure at time at t plus delta t divided by delta t. So that's just simply the gradient of excess flow pressure at that location. Similarly, we can work out what the differential u dz means, and this is the rate of change of excess flow pressure with respect to z. Now, in this case, we're looking at partial differential form here. The j term here is going to be the same. So we're looking at differentiating u with respect to z where time is constant. So in that case, we've got a flow pressure excess du dz can be written as u at some node I plus 1, which is minus the flow pressure at node I divided by delta z. So that's simply just approximating that equation like that. And obviously, it is an exact solution when delta t and delta z are very small terms. It's exactly equal to the correct answer. But it doesn't have to be perfectly accurate to give us a good solution using this numerical technique. Now, the next thing is, the last component, I suppose, is to now be able to work out what d2 u dz squared is. So what we need to do is to differentiate this term here in numerical form, and that's what's written down here. Again, I don't need you to go and derive these equations, but I need you to understand how you get them, because, as I say, it's a very useful technique in practice to be able to just, because a lot of practitioners forget how to solve partial differential equations. They might have done it, a particular equation for a while, but this technique is simple because what we can do is basically solve problems numerically. So we end up, in terms of the u dz here, the 2 u dz squared here, we differentiate the first part of the term here with respect to z. So that's u at I plus ij minus u at ij, and then we have to divide by delta z again. And then the other term here, we can write that as u I comma j as the node above that. This is node I, the node minus the current node. This is the current node minus the node above. And that's obviously we need to do that kind of approximation if we're going to actually try and differentiate this numerically. So we represent that term d2 dz squared like that, which can be rewritten in this way. And then we write out the entire equation, which is basically du dt, which is equal to this term, is equal to cv times d2 u dz squared, which is equal to that term. And when we do that, we end up with this equation here, which gives us the express flow pressure at node I, at time increment j plus 1, written in terms of all of these numbers here, which are all calculated at time increment j. So it means if we know the solution at any given time increment j, we can use all that information to find the flow pressure at the next time increment j plus 1. And once we've done that at all of those j plus 1 times, we can then solve the next time increment using that original value. In an Excel spreadsheet, it doesn't need to copy across the formula and provide a solution. So what we see is, as I say, the u at ij is the excess flow pressure at any node I and time increment j. And then these other values. We'll do an example in a second. But there's this number beta, which is important, where basically we need to make sure for conversions that our beta value, beta is less than half for conversions. So that puts a constraint on the numbers we're using, because we need to change the value of delta t and delta z. We can't just use arbitrary numbers of delta t and delta z. We need to make sure that we always have this number beta less than a half, otherwise you don't get a conversion solution. So that's usually not a major imposition. We usually have to do it by hand, but now, because of values of delta t and delta z. So obviously, the lower they are, the more accurate the solution is. But if you actually, what you can see here, if you've got a low value of delta z, this term here is going to get much higher. In which case, you would need a very low value of delta t. And if that was the case, if you wanted to get the answer after a year, and your delta t value was like 0.1 of a second, then you need many iterations to get your solution. So it's never usually that bad. But anyways, that's, and I'll show you an example in a second. Now there's one other boundary constraint which happens. Now very often there's cases where you may not have a drainage boundary at the base of your sample. So coming back to our original example here, where we had a sample, and this would be at the feeder and along where we had drainage, free drainage, no excess core pressures at the top of all of our samples, and that excess core meaning that we were driving the flow by high core pressure, high excess core pressure, to no excess core pressure at those boundaries. So if we've got a full, if we've got it sitting on a rock, for example, or in a bunker where we don't have any core assist at the bottom of our sample, then the only way the water can actually drain is vertically upwards. So to look at that situation, which we come across in practice, we need to set a new boundary condition given here, and the boundary condition corresponds to that condition at that boundary is the rate of change of u with respect to z is equal to 0. So essentially the gradient of u at that impermeable boundary is equal to 0. So when we go back to our equation for delta u, du, dz, when we look at that, it means that basically the only way we can actually do it numerically is just imagine a point on the other side of the boundary, and so that we can then equate a point here with a point here, and that forces the gradient to equal to 0. At the end of the day, it's all due to the equation we would use. It would mean that when we actually do that, when we make this substitution into our equation for du dz, we get a different equation here for the actual value of excess core pressure at that particular node. So we're solving du dt is equal to 3d times the du dz squared, but with du dz equal to 0, meaning we've got ui minus 1j is equal to ui plus 1j. Substitute that into those other equations, and this equation here will reduce to this equation here. So we get a slightly different equation corresponding to that node on the particular boundary of our problem. So this would be the general equation, and this is an equation which we would need to apply just for our node at the location of an impermeable boundary. And obviously, if you change that node, that's going to influence all of the other nodes, and then obviously then you get a different solution to your problem. Okay, so now let's look at an example. This is a little bit of an artificial example, but it's fine for demonstration purposes. But so what we're asked here, we're given sort of an excess core pressure dissipation that looks like this. So we've got in somehow, for example, we have a stand 5 picometers located in this 8 meter thick deposit of soft clay, and you found out you may have done a prediction, or you may have actually measured your core pressure distribution at some instance in time is equal to, it looks like this number here. We're reducing to 20 at the bottom, 30, 60, 90, and 100 at the very top. Now, in our example, we have to make some assumption, or we need information. So we've been provided the fact that we've measured the CV of the material, because the clay is 10 meters squared per year. That's the usual units used for CV, because they end up being like quite small numbers when you use different units. So they're quite useful. You just have to probably get used to using, converting this back to seconds if you need to, or any other time. Now we're asked to find the excess core pressures after 6 months. So what I'm going to say is, for this particular example, is that the time increment we're using is 1 month. So that would mean to get to a value of 6 months, we would need to do calculations. We need to do 6 iterations. So the first iteration will give us a value of 1 month. We would use that information to derive the values for the second month, and then the third, fourth, and fifth, and then finally the 6th month. So that will be 6 iterations from our initial condition. Now, in terms of how you would set this problem up, I'll just concentrate first of all on what we've got originally, because everything obviously depends on the initial values. Because once you've got these values, you remember the equations will give you the values of excess core pressures at the next time increment, and then once you've got those, you can go to the next time increment after that. The j equal to 0 is the initial condition. This is the initial time, and what we have here with 190.60. So what we've selected here is we've got delta z is equal to 2 meters. You can see here for this case, delta z is 2 meters, and delta t 1, we find beta value is 1.2, so that's fine. So we're going to get convergent solution, and this is we've got impermeable boundary here at the base of our problem. But at the surface of our problem here, which is quite common, you've got full drainage. Now, unfortunately, the program, or not the program, but the methodology requires you to set that core pressure on any boundary that's permeable to 0, because by definition, within a millisecond of that core pressure being 100, it would drop to 0. So in reality, you would never actually possibly even measure excess core pressure of 100 at a boundary like this. It would immediately drop to 0. So that's what we've inputted here. This value is 0 at node I equal to 0, which is the uppermost node, and then we've got 90, 30, 60, etc. So we get those numbers. Now the next thing is we then want to go. Once we set up a problem like that, and normally, as I said, this is kind of an artificial problem. You would never measure 100, so you would be given in any instance that would be a 0 value at the surface anyway, so you wouldn't have even guessed that that's equal to 100. Except, for example, in an odometer test, if you were making that prediction, we go back to our initial example here, the initial excess flow pressure, just at this boundary, in an odometer test, is equal to the applied stress. But we know that immediately that flow pressure is going to drop to 0. So if you were doing applying a different solution for an odometer test, you would have to force that top node, and actually if it was a free draining boundary at the bottom, and the bottom node to a 0 when you're doing the final different solution for that particular problem. So now we need to now use our equations, which is the equation to go and solve the values of the time increment j equal to 1. So how do we do it? And kind of like the equation is actually probably more cumbersome than it's easier to just try and remember what you do. And what you do here, and I've given you just various examples here, if I want to calculate this number here, you say it's equal to uij, which is this number, plus beta, which is this number, times this number, plus this number, minus twice that number. So calculate this number, it's equal to that number, plus beta times that number, plus that number, minus twice that number. When we calculate 34.2, I got that by saying equal to that number, plus beta, times that number, plus that number,
What the
minus twice
fuck
that number.
was this number, that number?
You will put in an Excel spreadsheet, and you just copy it onwards. Now lastly, for this particular problem here, in this some examples here, you can go through to work out how these numbers came about. But when we're looking at calculating this one, we now need to remember that we're actually at a different boundary condition where the UD is equal to 0. So therefore, we need to make use of the other equation, which will be also given in any formula sheet you'll be working with anyway, is basically this number is equal to, we calculate this number 24.2 as equal to that number, plus beta times twice this number minus twice that number. And that's how you get that value. Now ultimately, okay, so then you calculate it after one time increment. Now you use these numbers to find the values of excess flow pressure at the second time increment. So for example, we derive 55.7 is equal to that number, 60, plus beta, 0.2, times this number, 65, plus 34.2, minus twice 60. And we do the same for 7.5 is 34.2, plus 4.2 times 60, plus 24.2 minus 24.2 to give us this number. And then and obviously the bottom one here, we also have to apply the special boundary condition. So 28.3 is equal to 24.2, plus beta times twice 34.2 minus twice 24.2 will be 28.3. And you can see even in this example, the actual excess flow pressure are increasing. Normally, you will get reduction, but this is kind of an unusual example that the excess flow pressure increase and then subsequently they end up reducing finally. Now, the actual so after 6 time increments, so we calculate 2 months, 3 months we use a 2 months data, 4 months we use a 3 months data, and we get to the 6th j to the 6th, which corresponds to the time at which we want to calculate our excess flow pressure. 6 time increments in 1 month gives us this is our answer. So if we follow the actual number we get is initially we have our solution looks like this is our excess flow pressure variation. And you can see because of the actual way this problem is set up, you end up with actual excess flow pressures increasing near the bottom of the slope here, with the bottom of the table. Okay, so that's, and there's an example, obviously, you're doing an example like this at your practice session, you can bring your laptop, because you can play around with that laptop, and you can see that these equations are perfectly suited to just putting in each column, you put in the formula, which you can then copy into the next line, and copy that formula. So once you then put in the first formula here, then you can copy across again as many time increments as you want to derive your solution. Okay, so what we're now talking about is we've calculated how to work out what the excess flow pressures are based on a final different solution for this problem. Now we want to see, well, how do we use that information to work out how much secondary to the ground experience as a result of that excess flow pressure dissipation, which ultimately leads to an increase in effective stress, which causes settling. We'll come back to other aspects about average debate consolidation in a minute. I just want to get through and I'll just write down here settlement. And then we will find that difference. So okay, so what you may remember from the past is that we've got, in fact, we talked about it in about week 3 or 4, the typical relationship between void ratio and vertical effective stress for soil looks a bit like something like this and this here, where you get an initially stiff portion, which is our slope equal to CS. Once you pass the yield stress, which is sometimes called the pre-consolidation pressure or the vertical yield stress, once we pass that point, we end up going into
他妈的相同的东西，这个逼老师他讲的这么复杂了，我操！操你奶奶！接点水出来接着弄。 烟雾缭绕，缭绕。也和怎么搞的？
is still going to the CC. This sorry, this should be log scale. Consolidated. So when the sigma V dash is greater than sigma dash Vy and peak consolidation pressure, you get non-consolidated behavior. So the void ratio should also be sort of considered to be similar to the actual equivalent to another second. We'll come back to that point in a second. But the void ratio, obviously, as the void ratio reduces, you would imagine you're getting sediment increases. So first of all, let's look at, if we imagine, put down a few points here. If we wanted to go from, I'll just call it point A, B, C, D. These are points on this chart here. And if we wanted to work out, well, first of all, what's the strain? Actually, I'll write out first. Vertical strain, Ez, is equal to the change in void ratio over 1 plus the void ratio. Now, just so you can probably remember, that's equal to the void ratio is the volume of voids divided by the volume of solids. So that's the volume of voids, and the volume of, in our case, is actually equal to the volume of water. And the volume of soil is constant in our system. Soil is changing, the soil is there, it's not going anywhere, so that's a constant. And 1 plus the void ratio can be written as volume of voids plus the volume of soil over the volume of soil. So it's 1 plus VB over VS, or VB plus VS over VS. So that works out to be the change in the volume of voids over the total volume. Now, in terms of one-dimensional situation, that's equal to the change in height over the original height, and because we've got a 1D situation. That's the first thing we need to know. So that's why when we look at the change in void ratio, we actually can then get a corresponding strain in the soil, and that's the relationship between void ratio change and strain in the soil. So now let's look at various void ratio changes. So if we go from A to B, the change in void ratio between A and B is equal to CS times the log of sigma B dash at B minus CS times the log of sigma dash BA. And that's equal to CS times the log of sigma B dash over sigma B dash. So if we know the equation of this line is basically a linear line on a log scale here. The void ratio at A is some constant times CS times the log of sigma dash BA, whereas at point B, the same constant times the log of sigma dash the vertical vector stress at point B. We look at the difference between the two, the constant is eliminated, so we get this equation here, which can be rewritten simply as this equation here. So we want to go from, I'll just write an easy one, C to D. The delta E from C to D is exactly the same, except now we're on a different line here, which is equal to CC as opposed to CS. So in that case, the change in void ratio is equal to delta dash BD over BD, which is the final vertical vector stress on D, over vertical vector stress on C. So that's that line here. So, and if we wanted to change this to strain, we can just I'll write down here EC is a constant, that's equal to 1 plus E. Then we have to divide that by 1 plus E as well, and that's equal to 1 plus E. That means that's a strain. If we wanted to calculate the strain in a particular situation where the vertical effective stress is equal to sigma dash VC, and we're on the normal consolidated line along here, and the vertical effective stress increases to sigma dash VD, then we do that equation. And then if we want to go from, let's say, A to C, or maybe just go A to D, for example, we want to calculate what that strain is. So that's equal to the change in void ratio, we call this point Y, which is basically the yield point. We could say delta E between A and Y plus delta E between Y and D all over 1 plus E. So we're looking at the void ratio change, you go from A to Y, and then the void ratio change, you go from Y to D. As you go from void ratio from A to Y, it's exactly similar to going from A to B. That's equal to CS over 1 plus E times the log of sigma dash BY over sigma dash BA. Plus, as we go then from Y to D, we're going from, that's equal to CC over 1 plus E times the final vertical effective stress sigma dash BD over sigma dash BY. So, unlike the examples from A to B and C to D, when you go from A to D, you cross over the pre-consolidation pressure on the vertical yield stress, and you need to divide your equation for calculating strains into two different components. One is a component from A to Y, and the other is a component from Y to D. So, what we're going to do now is we're going to say, okay, well, we need, in our particular example, we need, if we're looking at a situation involving consolidation, we're going to predict core pressures in our problem, and we're going to actually work out what our effective stresses are. So what I want to do here is, we look at example 7.2 in your note, but we're not actually looking at example 7.2. We're going to use, I'll write down here, example 7.2, but no surcharge. Don't worry about surcharge, or we'll talk about surcharging at our next lecture. But what I'm doing here, what we're looking for in this example, is basically we're building, we've got a 6 meter flare here, and we're building an embankment which is 2 meters high. This is our embankment, which is 2 meters. And the unit weight of that is equal to 18. So essentially we're applying vertical stress to the surface of our 6 meter clay layer of equal to 2 times 18, which is equal to 36. And what we're being asked here is, in this example, what in this example I'm just doing now is, what is the settlement? Determine the consolidation settlement, and so determine the consolidation. That particular layer. So that's all we're doing. Now, in this particular example, because we're applying, and I suppose it's like, I haven't really solved, oh, sorry, after 0.6 of the year. Okay, so what sorry, I'm trying to put corners there by using an example. Maybe I'll just do this anyway, and just do it off the top of my head. So what we want to do here, in this example, is we want to actually go and predict this consolidation settlement of this after 0.6 of the year. So what we've got here is a layer where we've got essentially 32 kPa applied to our soil. We've got an impermeable boundary in our particular problem. So our excess core pressure field will look basically, I imagine dividing my layer into what do we do? We do 3 layers. That makes it quite easy. So now in our particular problem here, so we've got what we've got is we've got an initial vertical effective stress. We've been given the unit weight of the material the clay is gamma is equal to 16 Newton per cubic meter. So first of all, because this is mostly covering about core pressure dissipation, but this is maybe no 0, 1, 2, 3. We've got a value here equal to delta Z, and that's equal to 2 meters. We just showed delta Z is equal to 2 meters, and our CD value in our clay is equal to 5 meters squared per year. So if we now look at our node 1, 0, 1, 2, 3, and actually I should calculate our beta value. So if we're looking at imagine we've got right down here, delta T is equal to 0.2 years. So beta, so in other words, if we want to calculate our values at 0.6 of a year, that means we need 3 iterations. So beta will equal to CD times delta T. If we got delta Z equal to 2 meters of delta Z squared, and that's equal to 5 times, again, knowing everything is in years in terms of time, over 2 squared, and that's equal to 1.25. So that's what we need to calculate our excess core pressures. And this is a time t equal to 0, which corresponds to the first time increment. Now, when we apply, in this example, we apply a vertical pressure of 32. If we have a wide enough embankment, you can assume that the excess core pressure right through the layer is equal to 32 kPa. So we can say that initially this 32 value will go to 0 at the surface, but then it drops down to 32, 32, and 32. And so that will give us a value of and this is a time equal to 0.2 of the year, and we've got time 1.4, time equal to 0.6. Now from this example, we can work out what the value of each of these excess core pressures are at this location. So for example, at this location here, this number here is going to be 32 plus beta, and I'm going to have to give you, because I'm making up this problem as we speak, I need to go and I'll do a solution for this, and I'll post it on LMS. But what you do here, rather than making up numbers as I go along, this number here would equal to 32 plus beta, which is 0.25 times 0 plus 32 minus 532. Similarly, this number will be 32 plus beta times 32 minus 32 will not change. And this number is also going to be similar. So we will end up calculating our excess core pressures corresponding to that situation. And I haven't done the calculation yet for this simplified problem, but I will do, and like I say, I'll put that on the web. Now, the main point I want to get to here, so that you can actually do your assignment or fact question tomorrow, is we've got excess core pressures at various locations. And I'm going to call that A, B, C, and D. And these are some numbers I've actually gone and calculated for our particular problem. Now, how do I actually, we've been told, for this, so I'll carry on here, for this problem, the OCR is equal to 1. And therefore, when the OCR is equal to 1, we're always going to be using this equation here, because we're going to be going along this normal consolidation line. From C to D, the change in the strain is going to be the change in void ratio over 1 plus the void ratio. So for this problem, the OCR value is equal to 1, so that the vertical strain is equal to CC over 1 plus E times the log of the final vertical effective stress over the initial vertical effective stress. So this is a final sigma D dash, which is equal to, in our case, because we're trying to find the settlement after 0.6 of a year, this is our problem here, that's the sigma D dash at T equal to 0.6 of a year. And this value here is the initial sigma D dash. So finally, I'll write down our nodes again. So it's node 0, 1, 2, and 3. And what we're saying here is the excess, write down here, the excess core pressure we've calculated from our finite difference solution here. And we're saying this is equal to some numbers, A, in fact, we know A is 0, and B, C, and D. Now, the first thing we need to do is to work out, if we want to do our calculation, we need to know what is sigma dash df and what is sigma dash di. But the easy one here, calculate sigma dash di, it's simply equal to the actual initial vertical effective stress for our problem. So we've got a uniweighted soil, this is before the embankment was built. So at 1 meter depth here, for example, sigma d dash is going to be twice times 16 minus, now the water table is at the ground surface, minus twice times 10, and that's equal to 12 kPa. Similarly, at 0.2, so that's initial value, sigma b initial is going to be 4 times 16 minus 4 times 10 is equal to 24 kPa. What we need to do is write down our vertical effective stress corresponding to the initial conditions. Now, 0, change that as well. So that's equal to 12 kPa, 24 kPa, and 36 kPa. Now, as we'll see in a minute, when you're calculating these strain values and you divide that by 0 at the very surface, you run into problems because you're going to be dividing them by 0. So just on that boundary, we're going to have a situation where normally, just in practice, you would increase that number to just unit to the value of 1. 1 kPa is a very low stress anyway, so you increase that value to 1 to give you that value of strain. Now, how do we actually go and calculate sigma dash df? It's equal to the actual value of, okay, so we've applied, I'll just write that down here, we've applied stress of 32 kPa. So we've increased, that means we've increased, if all of these excess core pressures were 0, the increase in effective stress that we'll be experiencing will be 32. However, because they're not 0, we haven't actually increased the effective stress at these points by that amount. So the increased effective stress, increase sigma b dash, which is equal to delta sigma b dash, is equal to delta sigma b minus delta u. So if we've applied a value of 32 kPa, this is going to be 32 minus delta u, and that means the final vertical effective stress is going to be equal to the initial value of vertical effective stress plus the incremental increase in vertical effective stress, which will be 32 minus delta u. Let me just have a think about that. Essentially, if you're looking at this problem, like you may have seen examples like this last year's unit, you would basically assume for the full consolidation settlement, this final vertical effective stress would basically be equal to the initial vertical effective stress plus 32 kPa, which is the amount we applied. Now, however, in this example, because there's remaining excess flow pressures, you actually need to go and the vertical effective stresses are not equal to that number. So here, the initial vertical effective stress at surface is equal to 0 plus 32 minus the excess flow pressures, which is, I'll write down here just for the sake of it. We know that A is 0, but that's the final vertical effective stress. In this case, it's going to be initial vertical effective stress is 12 plus 32 is 44. Is 44 minus 12, and this will be 24 and 32, which is 56 minus 24 minus B, 56 minus C, and 36 plus 30 is 68 minus D. Nearly there, and like I say, apologize, I'm going to write out the full solution for this and put it on the list, but I may as well just continue now. So we calculate the strain is going to be CC over 1 plus E as the log of the final vertical effective stress over the initial vertical effective stress. So we calculate all of these numbers corresponding to the strain at that particular node. And then to calculate the settlements, we basically allow, again, this is another part of our sort of simplification, is we need to actually go, if you imagine, I'll just draw it out again, we've simplified our 6 meter soil deposit into this type of situation. And what we're saying is, this top node here is representative of the upper meter of soil. You can say, well, that's clearly not true, but it's an approximation, and we're doing it by hand with obviously bigger values of delta Z than what we might be doing numerically. Solution, the strains are calculated at node 1 correspond to this thickness of layer, which happens to be 2 meters. You can say at node 3, the thickness of layer corresponding to that is this one, and bottom one is equal to 1 meter. So I'll just call this H. We call that H equal to 1 meter, and H is equal to 2 meters, 2 meters, and 2 meters. Now the actual settlement, in last point here, the settlement is the strain times the thickness of the layer. So the settlement of layer I is equal to the strain times the thickness of that particular layer, HI. So what we need to do, the overall settlement then, is basically the sum, this is layer I, of all these EZI times HI. So the actual overall settlement of our embankment will be the compression of each of those 4 particular layers of our material. So to recap again, and like I say, I'll write out the solution in full for you, but you do an example very similar to this tomorrow as well for your practice session. So the hard way to work out what the final vertical effective stresses are, you determine that from your excess core pressure distributions that you've calculated. And once you've done that, you then calculate it, you look at the equation for strain, which you've got, and then you look at the layer associated with each of those nodes at which you calculated those strains, and then get the product of the layer thickness of those particular strains, sum them all together to get the overall settlement. Okay, I've gone on a long time, so sorry about that. So, like I say, the solution will be there. Hopefully, you'll get reinforced. There's a lot covered in today's lecture. Laboratories.
操他妈2个小时才他妈都睡觉了，真鸡巴困死了！明天他妈的我看看，我等于说这2个5507看不懂，4401还看不懂，他妈问题大了！我他妈过2天还有课看不懂，还是不是最大的问题？最大的问题是明天他妈后天2个实验你把它给写完，操！就这吧，拜拜。